Look up on a clear night, far from city lights, and the sky does something that no textbook fully prepares you for. It moves. Not in the slow, majestic sweep of a planet tracing its arc across the ecliptic, not in the dignified rotation of the celestial sphere overhead, but in a rapid, almost nervous flickering. The stars tremble. They pulse with blue and white and faint red, shifting color in fractions of a second, as though each one is sending a coded signal across the dark. It is one of the most ancient optical experiences in human history, and for most of human history, no one knew why. The answer, when it finally came, did not diminish the phenomenon. It deepened it. Because the reason stars twinkle has nothing to do with the stars themselves. The stars are not blinking. They are not pulsing, not flickering, not changing. A star like our sun, sitting 93 million miles from Earth, that is approximately 149 million kilometers, is a sphere of plasma burning at 10,000 degrees Fahrenheit on its surface alone, fusing roughly 600 million metric tons of hydrogen into helium every single second. It does not blink. It cannot blink. It is a nuclear furnace so large that 1,300,000 Earths could fit inside it, and it has been burning continuously for 4.6 billion years. 4.6 billion years. If you compress the entire lifespan of our sun into a single 24-hour day, modern human civilization, everything from ancient Sumer to the present moment, would occupy the final 0.2 of 1 second before midnight. That star does not tremble. What trembles is everything between the star and your eye. The atmosphere surrounding Earth is not a uniform, stable, transparent medium. It is a churning, layered, thermally unstable ocean of gas. It has weather systems, jet streams moving at speeds exceeding 300 kilometers per hour, temperature gradients where cold polar air collides with warmer tropical masses, and microscopic turbulent eddies that spin and dissipate at scales too small to see but large enough to bend light. The column of air sitting above any single point on Earth's surface extends roughly 100 kilometers upward before fading into the near vacuum of space. That is, again, 100 kilometers, a distance you could drive on a flat road in about an hour. Yet within that 1 hour of vertical space, light arriving from a star billions of kilometers away must negotiate a gauntlet of constantly shifting refractive densities. Every pocket of warm air bends the light differently than the cold air beside it, and those pockets are never still. This process has a name. Astronomers call it astronomical scintillation. Atmospheric physicists call it optical turbulence. The rest of the world calls it twinkling. And the scientific machinery behind it touches some of the deepest principles in classical physics, optics, and fluid dynamics simultaneously. Now consider the planets. On the same clear night, if you know where to look, Jupiter hangs in the southern sky like a pale cream lantern, steady and unwavering. Mars burns a dull iron red without so much as a single flicker. Venus, when it appears near the horizon at dusk or dawn, blazes with a white intensity that makes it the third brightest object in Earth's sky after the sun and the moon. And it does not twinkle, not once. These objects pass through the exact same atmosphere, the same turbulent columns of air, the same jet streams and thermal inversions. They are subject to precisely the same physical laws. Yet they hold still. Why? The answer sits inside a concept that is deceptively simple once stated, and yet reshapes the way you look at the entire night sky. It is the concept of angular diameter, the apparent size of an object as seen from a given distance, not its physical size, but how large it appears to the eye or a telescope. A planet like Jupiter, despite sitting approximately 600 million kilometers from Earth at opposition, is large enough, 142,000 kilometers across, that it subtends a measurable angle in Earth's sky. Even to the naked eye, it is not a point, it is a tiny disk. Tiny, yes, about 50 arcseconds across at its closest approach, a unit of measurement where 1 arcsecond equals 1/3600th of 1 degree of sky. That sounds impossibly small. But in the physics of light refraction, it is the difference between a signal and silence. A star, by contrast, is almost always a perfect geometric point source. Proxima Centauri, the closest star to our solar system at 4.2 light-years away, roughly 40 trillion kilometers, a distance so extreme that a spacecraft traveling at the speed of the New Horizons probe, roughly 58,000 kilometers per hour, would need over 78,000 years to arrive, appears in the sky as an object with an angular diameter of less than 1/10,000th of one arcsecond. No telescope on Earth's surface can resolve it as anything other than a point of light. A single point. A laser dot against the infinite. When a point source of light passes through turbulent air, each atmospheric disturbance deflects the entire beam. The light arriving at your eye from that star comes through one infinitely narrow channel, and every time a pocket of warm air crosses that channel, the beam shifts, dims, brightens, or changes color depending on which wavelengths bend most. The result is the shimmer you see. Rapid, chaotic, beautiful. When that same turbulent air sits above a planetary disk, something fundamentally different happens. The planet's light does not arrive through a single channel. It arrives through thousands of channels simultaneously, each slightly offset from the others across that 50 arcsecond disk. Each channel suffers its own independent atmospheric distortion, but because there are so many of them, the distortions average out. One channel brightens as another dims. One bends left as another bends right. The net effect, as seen by your eye or a camera, is stability. The planet holds. The star trembles. This is not a quirk or an accident of geometry. It is a direct, measurable consequence of the wave nature of light interacting with a medium that violates spatial coherence. That is, a medium where the refractive index varies differently at every point in space. The coherence radius, known in physics as the Fried parameter after the American physicist David L. Fried, who formalized the mathematics in 1966, defines the spatial scale over which the atmosphere can be treated as uniform. Above a good astronomical site, this parameter typically ranges between 5 and 20 centimeters. Any light source whose projected beam on the atmosphere is smaller than this scale, meaning any true point source, is fully scrambled. Any source larger than this scale self-corrects. The stars are simply too far away. The universe has placed them so far beyond us that no amount of physical size compensates for the distance. Betelgeuse, the red supergiant in the constellation Orion, is so immense that if placed at the center of our solar system, it would engulf every planet out to Jupiter. Its diameter reaches approximately 1 billion kilometers. And yet, sitting approximately 700 light-years from Earth, it subtends only 56 milliarcseconds in the sky, small enough that for most purposes it behaves as a near-perfect point source. On nights of poor atmospheric seeing, even Betelgeuse flickers. There is a myth worth addressing directly. Many people believe that stars twinkle because they are small, or because they are somehow intrinsically unstable objects. The sun, after all, does have real surface activity, solar flares, coronal mass ejections, sunspot cycles lasting approximately 11 years, but none of that activity is what causes the stars in the night sky to scintillate. The twinkling you observe has zero physical origin in the stars themselves. It is entirely a property of Earth's atmosphere. If you remove the atmosphere, placed yourself in low Earth orbit with nothing but the vacuum of space between you and the stars, the entire sky would go silent and steady. Every star, without exception, would burn with a cold, unwavering, crystalline light. No shimmer, no pulse, no color shift. This is precisely what astronauts aboard the International Space Station report. 350 kilometers above Earth's surface, above virtually all of the atmosphere's optical turbulence, the stars do not twinkle. They are fixed, hard points of absolute brilliance against absolute black. The experience, by multiple accounts, is simultaneously more beautiful and more unsettling than the twinkling sky below. Beauty, it turns out, is sometimes an artifact of our own limitations. The deeper question, the one that has driven astronomers for centuries, is not merely why stars twinkle, but what that twinkling contains. What information is encoded in the shimmer? And when scientists began building machines to decode that turbulence rather than simply compensate for it, they discovered something that changed the entire field of observational astronomy. That discovery did not come easily. It came after decades of failed observations, blurred images, and a frustration so fundamental that it forced astronomers to rethink where they built their telescopes, how they designed their instruments, and ultimately, whether the ground was the right place to look at all. The atmosphere is, in the most literal sense, a lens. Not a clean, ground glass lens sitting inside a precision optical instrument, but a turbulent, breathing, restless medium that distorts everything passing through it. For most of human history, the stargazer accepted this distortion as simply the nature of the night sky. The shimmer was the sky. It was not a problem to solve. It was a feature of the universe. That assumption held for roughly 4,000 years of recorded astronomical observation. The ancient Egyptians tracked stellar risings with extraordinary precision. The heliacal rising of Sirius, the brightest star in the night sky, marked the beginning of the flooding season of the Nile with an accuracy that still commands respect. Babylonian astronomers in Mesopotamia, working between roughly 1800 and 400 BCE, compiled cuneiform tablets cataloging planetary motions with a mathematical rigor that would not be surpassed in the Western world for over a millennium. The Greeks built geometric models of the cosmos. Islamic astronomers of the 9th through 13th centuries refined those models, corrected Ptolemy's errors, and named most of the stars whose Arabic designations we still use today. Betelgeuse from Yad al-Jawza, meaning the hand of the giant. Aldebaran from Aldebaran, the follower. All of this knowledge accumulated under a sky that shimmered. Nobody asked why. The shimmer was simply there. The question only became urgent when it became an obstacle. Galileo Galilei pointed a refracting telescope at the night sky in 1609 and changed the relationship between humanity and the cosmos in a single winter. Jupiter had moons. The moon had mountains. The Milky Way dissolved into individual stars too numerous to count. The telescope was not merely a tool, it was an argument. An argument that the universe contained structure beyond the resolution of the naked eye, and that magnification would reveal it. Galileo's instrument magnified approximately 20 times. Within decades, telescopes grew larger, longer, and more powerful. By the mid-17th century, astronomers were building instruments with focal lengths measured in meters, then tens of meters. The pursuit was simple: more aperture, more light, more resolution. The sky refused to cooperate. No matter how large the telescope grew, the stars stubbornly refused to resolve into disks. They remained points. Bright, trembling, irresolvable points of light. The images blurred. Long exposure observations smeared. What the telescope revealed in terms of raw light-gathering power, it surrendered in terms of sharpness. The theoretical resolution of a large telescope, determined by a relationship known as the Rayleigh criterion, where the minimum resolvable angle in arcseconds equals approximately 252 divided by the aperture in millimeters, suggested that a telescope with an aperture of 1 meter should resolve details as fine as 1/10 of an arcsecond. In practice, from the ground, almost no telescope ever achieved better than 1 arcsecond of resolution on a typical night. The atmosphere was quietly, invisibly, relentlessly erasing the advantage of every additional centimeter of glass. Isaac Newton understood this, at least partially. In his Optics, published in 1704, he wrote that the trembling of the stars arose from the unequal densities of the air, and he suggested, with a characteristic bluntness, that the only solution was to observe from elevated locations, above the densest and most turbulent layers. He was right. He was also 3 centuries ahead of the infrastructure required to act on his insight in full. What Newton could not have known was the precise physical mechanism responsible. That understanding would require the development of the wave theory of light, the mathematics of fluid turbulence, and eventually the statistical theory of random processes, intellectual tools that did not exist in complete form until the 20th century. The wave theory of light, fully developed through the work of Christian Huygens in the 17th century, and Thomas Young's landmark double-slit experiment in 1801, established that light propagates as a wave. Young's experiment demonstrated interference, the phenomenon where 2 waves meeting in phase reinforce each other, and 2 waves meeting out of phase cancel each other, with a simplicity so elegant that it settled the wave versus particle debate for over a century. Light, spreading outward from a source, arrives not as a stream of billiard balls, but as an advancing wavefront, an infinitely thin surface of constant phase. Now consider what happens to that wavefront when it enters Earth's atmosphere. A wavefront arriving from a distant star is, for all practical purposes, perfectly flat by the time it reaches the top of the atmosphere. The star is so far away that its light, which left as a spherical wave expanding outward in all directions, has had trillions of kilometers to flatten. At the scale of Earth, a sphere roughly 12,700 kilometers in diameter, the incoming wavefront from even a nearby star is geometrically indistinguishable from a perfect plane wave. Think of ocean swells arriving at a shoreline from a storm that originated thousands of kilometers away. By the time those swells reach land, they move in nearly parallel lines. They have forgotten the chaotic point where they began. That flat, orderly wavefront hits the atmosphere and immediately begins to fracture. The refractive index of air, the measure of how much the medium slows and bends light relative to its speed in a vacuum, is not constant. It varies with temperature, pressure, and humidity. At sea level, the refractive index of dry air at standard temperature and pressure is approximately 1.000293. This number sounds nearly identical to 1, the refractive index of a perfect vacuum, and in terms of everyday optics, the difference is tiny. But across a column of atmosphere 100 kilometers deep, even fractional variations in this number, distributed unevenly in space and fluctuating rapidly in time, are enough to introduce measurable phase differences across the wavefront. Each parcel of air at a slightly different temperature bends the incoming light by a slightly different amount. The flat wavefront, after passing through the full depth of the atmosphere, arrives at the ground wrinkled. Corrugated. Its phase varies from point to point across the aperture of any telescope trying to collect it. Different parts of the incoming wave have traveled, in effect, slightly different path lengths to arrive at the same focal point. Some have been slightly accelerated, others slightly retarded. When these misaligned wave segments are brought together by a telescope mirror or lens to form an image, they interfere, sometimes constructively, producing a momentary bright speckle, sometimes destructively, producing a momentary dimming. The image dances. The star appears to move, change brightness, and shift color on timescales of milliseconds. This is atmospheric scintillation, described in full wave optical terms. The timescale of the fluctuation, typically between 10 and 100 milliseconds, is set not by the stars, but by the wind speed at the turbulent layer, usually the tropopause at roughly 10 to 12 kilometers altitude, where the jet stream introduces the strongest phase distortions. The physical size of the individual turbulent eddies responsible for most of the seeing degradation falls between a few centimeters and a few tens of centimeters. The fried parameter again, that critical coherence length that determines whether a given aperture will be limited by the atmosphere or by diffraction. For a human eye, with a pupil diameter of roughly 6 to 8 millimeters, the fried parameter is almost always larger than the aperture. This means the human eye typically receives a coherent patch of wavefront, one that has not been significantly broken up by turbulence. The star twinkles because that small coherent patch is being redirected, tipped, tilted, moved as a unit by the large-scale atmospheric motions. The entire image jumps around a mean position. The brightness fluctuates, the colors separate. The experience is genuine, beautiful, and physically real. For a large telescope, with an aperture of 1, 4, or 10 meters, the situation is entirely different. The aperture now collects hundreds or thousands of independent coherent cells simultaneously, each with its own phase error. The image does not jump. It spreads into a blurred, speckled halo. The technical term is the seeing disk, and its diameter at a mediocre site might reach 3 arcseconds, at a good site perhaps 1 arcsecond, at the world's best high-altitude observatories perhaps half an arcsecond on an exceptional night. Half an arcsecond. That is still 5 times worse than what the same telescope could achieve above the atmosphere. The realization of this gap, between what ground-based telescopes theoretically could resolve and what the atmosphere actually permitted, accumulated slowly through the 19th and early 20th centuries. The photographs were blurry. The measurements were noisy. The light curves of variable stars jittered. And as photographic emulsions improved and electronic detectors replaced the human eye at the telescope eyepiece, the atmospheric ceiling became impossible to ignore. The most consequential early attempt to measure and characterize the ceiling came not from an observatory, but from military research. During and after the Second World War, defense agencies in the United States and the Soviet Union became deeply interested in the same physical problem for an entirely different reason. Atmospheric turbulence was not merely degrading astronomical images, it was degrading reconnaissance. Satellites and high-altitude aircraft photographing ground targets through the atmosphere encountered the same turbulent distortions that blurred the stars. The physics was identical. The aperture was different. The urgency was acute. The classified research that followed, much of it declassified only decades later, produced some of the most mathematically rigorous characterizations of atmospheric optical turbulence ever written. Among the foundational contributions was the statistical theory developed by Soviet mathematician Andrei Kolmogorov in 1941, initially conceived to describe fluid turbulence in general terms. Kolmogorov's turbulence theory described how kinetic energy injected at large scales cascades down through progressively smaller eddies in a predictable statistical hierarchy, what physicists call the turbulent cascade. Applied to atmospheric optics, Kolmogorov's framework predicted the statistical structure of the phase distortions imposed on an incoming wavefront with remarkable accuracy. The predictions matched observations. The mathematics worked, and buried within that mathematics was a deeply unsettling implication. The problem was not going to be solved by building larger telescopes on the ground. The atmosphere would always win. Unless somehow the atmosphere could be removed from the equation entirely, or corrected for in real time faster than it changed. Both paths were pursued. Both led to technologies that did not yet exist. And the race to build them would redefine what it meant to look at the sky. The Fried parameter is a number, a single number measured in centimeters that determines whether a night of observation is worth anything at all. On a mediocre night above a sea level site, it might reach 5 centimeters. On an exceptional night above the best high-altitude observatory on Earth, it might reach 25 or 30 centimeters. The aperture of the Very Large Telescope in Chile, each of its 4 primary mirrors measuring 8.2 meters across, is approximately 328 centimeters. The ratio between what the atmosphere allows and what the instrument demands, on even a good night, is somewhere between 10 and 60 to 1. The atmosphere wins, every single night, by an enormous margin. The only honest response to that margin was to understand it completely, down to its physical roots, before any engineer could hope to fight it. Light travels through a vacuum at 299,792,458 meters per second. Exactly. This value is now the definition of the meter, fixed by international agreement in 1983. The meter is defined as the distance light travels in a vacuum in 1/299 millionth of a second, making the speed of light a constant by definition rather than a measurement. When light enters any transparent medium denser than vacuum, glass, water, or air, it slows. The ratio of the speed of light in vacuum to its speed in the medium is the refractive index. For optical glass, this value typically falls between 1.4 and 1.9. For air at sea level, as noted earlier, it is approximately 1.000293. The difference from vacuum is tiny, but it is not zero, and it is not uniform. The refractive index of air depends primarily on its density, which in turn depends on temperature and pressure following the ideal gas law. For dry air, the relationship between refractive index and temperature is approximately linear over the range of temperatures encountered in the lower and middle atmosphere. A temperature increase of 1 degree Celsius at constant pressure reduces the refractive index by roughly 1 part per million. 1 part per million sounds negligible. Across a turbulent atmospheric column where temperature fluctuations of several degrees occur over spatial scales of centimeters to meters, the cumulative optical path difference introduced across the aperture of a large telescope can reach several micrometers, several wavelengths of visible light, and a phase error of 1 full wavelength is already enough to destroy diffraction-limited image quality entirely. Visible light spans wavelengths from roughly 380 nanometers at the violet end to about 750 nanometers at the deep red end. 1 nanometer is 1 billionth of a meter. A human hair is approximately 80,000 nanometers wide. The wavelength of green light near the peak of human visual sensitivity is roughly 550 nanometers. When the atmosphere introduces path length differences of several micrometers, several thousand nanometers, across the wavefront arriving at a telescope, it is distorting the light by many times its own wavelength. The interference pattern produced at the focal plane is not an image. It is a scrambled mess of constructive and destructive interference, shifting and reforming on millisecond timescales. The turbulent structures responsible for this scrambling are not distributed uniformly through the atmosphere. They are concentrated in distinct layers, each with its own characteristic height, wind speed, and turbulence intensity. The dominant layer for optical turbulence at most sites is the surface boundary layer, the lowest few hundred meters of atmosphere, where contact with the ground generates mechanical and thermal turbulence as air flows over heated rock, soil, and vegetation. This layer is the reason observatories are built on mountains. Elevation lifts the telescope above the worst of the surface boundary layer and reduces the total air mass between the instrument and space. A telescope at 4,000 meters altitude sits above roughly 60% of Earth's atmosphere by mass. The air above it is thinner, drier, and substantially less turbulent than at sea level. The second dominant turbulence layer is the tropopause, the boundary between the troposphere and the stratosphere, sitting at roughly 10 to 12 kilometers altitude. This is where the jet stream lives, a narrow band of fast-moving air that can reach speeds of over 300 kilometers per hour, generating strong wind shear and Kelvin-Helmholtz instabilities at the shear boundary. Kelvin-Helmholtz instabilities are the atmospheric equivalent of waves forming on the surface of a river, where fast and slow water meet. They roll up into vortices, break down into turbulence, and cascade energy from large scales to small in exactly the pattern Kolmogorov's mathematics predicted. The visual signature of Kelvin-Helmholtz instability, parallel rows of breaking wave-like cloud formations, is occasionally visible in the sky and has been documented in satellite imagery around the world. Every one of those breaking waves is generating optical turbulence that an astronomer far below will measure as degraded seeing hours later. Above the tropopause, in the stratosphere and mesosphere, the air is far too thin to contribute significantly to optical turbulence. The problem is entirely confined to the lowest 12 kilometers of Earth's atmosphere, a layer so thin relative to Earth's radius of 6,371 kilometers that if Earth were the size of a standard desktop globe 30 centimeters in diameter, the relevant turbulent atmosphere would be a film less than half a millimeter thick. The entirety of the atmospheric seeing problem, the obstacle that defeated every ground-based observatory for 3 centuries, lives within that half millimeter of metaphorical film. Understanding this vertical structure was not merely academic. It had direct engineering consequences. If the turbulence was localized in layers, then measuring the height, strength, and wind velocity of each layer independently would allow, in principle, a complete characterization of the atmospheric distortion at any given moment. This characterization became the foundation of a discipline called optical turbulence profiling, pursued using instruments called SINDARs, scintillation detection and ranging devices, which function on a principle analogous to radar. A SIDAR points a telescope at a bright binary star, 2 stars separated by a known angular distance, and records the cross-correlation of the scintillation patterns produced by each star simultaneously. Because the 2 stars are separated by a known angle, turbulent layers at different altitudes produce cross-correlation peaks at positions that shift with height in a predictable geometric way. The altitude of each turbulent layer can be read directly from the position of its peak. The strength of the turbulence can be read from the peak's amplitude. The wind speed and direction can be extracted from how the peak moves over time. The result is a vertical profile of atmospheric optical turbulence, a complete map of where the problem lives and how severe it is at each altitude, updated in near real time. This profile is described mathematically through a quantity called the refractive index structure parameter, written as c sub n squared, which quantifies the variance of refractive index fluctuations at a given point in the atmosphere as a function of altitude. Integrating c sub n squared over the full atmospheric column gives the Fried parameter directly. Strong turbulence at many layers means a small Fried parameter and terrible seeing. Weak, well-separated turbulence confined to one or two thin layers means a larger fried parameter and better image quality. What the turbulence profiling data revealed, accumulated over decades of site testing campaigns on every major mountain proposed for observatory construction, was that the atmosphere has a personality. Each site has a characteristic turbulence profile shaped by local geography, prevailing wind patterns, and ocean or land surface temperatures. The summit of Mauna Kea in Hawaii, rising 4,205 meters above the Pacific Ocean, benefits from an exceptionally stable marine boundary layer below the summit inversion and relatively weak high-altitude turbulence for a significant fraction of the year. The Atacama Desert in northern Chile, at altitudes between 2,400 and 5,000 meters, offers some of the driest air on Earth and seeing conditions that rival or exceed Mauna Kea on the best nights. The Tibetan Plateau and the high Antarctic Plateau at Dome C, sitting at 3,233 meters elevation near the center of the Antarctic ice sheet, offer extraordinary free atmosphere seeing because the ice surface generates almost no thermal boundary layer turbulence, though the logistical challenges of operating there are severe. None of these sites, however perfect, eliminates the atmosphere. They minimize it. They select against the worst nights. They push the fried parameter from 5 centimeters toward 20 or 30, but even at 30 centimeters, the Very Large Telescope's 8.2-meter mirror is still collecting wavefront distortions across more than 27 independent coherent cells simultaneously. The image is still blurred. The diffraction limit, the theoretical resolution set by the wave optics of the aperture itself, is still unattainable. The diffraction limit of a telescope is set by a simple relationship. The minimum resolvable angular separation between two-point sources, in radians, is approximately 1.22 times the wavelength of light divided by the aperture diameter. For the Very Large Telescope observing at 550 nanometers, green light, with an 8.2-meter aperture, this works out to approximately 0.014 arc-seconds. On a superb night with a fried parameter of 20 centimeters, the atmospheric seeing limit is approximately 0.5 arc-seconds. The atmosphere is making the telescope perform 35 times worse than its theoretical capability. 35 times. As though all 8.2 meters of that precision ground glass were functionally reduced to a mirror 23 centimeters across, slightly larger than a standard dinner plate. This was the wall. Massive, precise, extraordinarily expensive instruments operating at a small fraction of their potential because of air. Because of the same physical phenomenon that makes a spoon appear bent in a glass of water, scaled up to atmospheric dimensions and rendered dynamic by wind and heat. The physics was completely understood. The mathematics was exact. And for a moment in the mid-20th century, it appeared that the only solution was the most radical one possible. Leave the atmosphere behind entirely. But before that solution could be built and launched, a different approach began taking shape in the minds of engineers and physicists who refused to accept that the atmosphere was an immovable obstacle. If the distortions could be measured in real time, could they also be corrected in real time? Could a mirror be made to change its shape fast enough and precisely enough to unwrinkle a wavefront that the atmosphere had spent 100 kilometers corrupting? The answer required a mirror that could flex, and it required a measurement system fast enough to keep up with an atmosphere that changed its mind every 10 milliseconds. Horace W. Babcock was not a household name. He spent the bulk of his career at the Mount Wilson and Palomar observatories in California, working on stellar magnetic fields and solar physics with the quiet precision of a man who believed that the most important problems in science were the ones nobody had yet figured out how to attack. In 1953, he published a paper in the Publications of the Astronomical Society of the Pacific that proposed, in complete technical detail, a system for compensating atmospheric turbulence in real time using a deformable optical element controlled by a feedback loop measuring the incoming wavefront distortion. The paper was titled "The Possibility of Compensating Astronomical Seeing." It described with remarkable accuracy every essential component of what would eventually be called adaptive optics: the wavefront sensor, the deformable mirror, the control computer, the closed feedback loop. The astronomical community read it, and then, largely, set it aside. Not because the idea was wrong. It was correct in every essential respect. The problem was that the technology required to implement it did not exist in 1953. The deformable mirror Babcock envisioned, a mirror surface that could reshape itself at hundreds of points simultaneously, hundreds of times per second, under precise electronic control, was beyond the manufacturing capability of the era. The wavefront sensor he described required detector arrays and computational speeds that were decades away. The control computer needed to process the sensor data and calculate the mirror corrections faster than the atmosphere changed, would have filled a large room and still been too slow. Babcock had written the blueprint for a machine that could not yet be built. The idea waited. For 20 years, it waited. The force that finally moved it off the page and into hardware was not scientific curiosity. It was the Cold War. By the early 1960s, the United States Air Force faced a surveillance problem of acute strategic importance. Soviet ballistic missile development was accelerating. Tracking missiles during boost phase, characterizing new rocket designs, and monitoring launch facilities required imaging from space or from high altitude. But satellite imaging in the early years of the space age was limited. Film return systems were slow, and the resolution achievable through the atmosphere from ground-based tracking telescopes was severely degraded by exactly the same seeing effects that tormented astronomers. A telescope that could see a Soviet missile clearly from a ground station in the continental United States would require solving the atmospheric turbulence problem in real time. The Air Force understood that Babcock's 1953 paper described a theoretical solution. They funded the engineering to build it. The program that followed was classified at the highest levels for over 3 decades, under the umbrella of what eventually became known as Project ITEC, and later a series of programs within the Air Force Weapons Laboratory in Albuquerque, New Mexico. Engineers and physicists built the first working adaptive optics systems through the 1960s and 70s. The deformable mirrors used piezoelectric actuators, materials that change physical dimensions when a voltage is applied across them, by amounts as small as a few nanometers per volt, with response times measured in microseconds. An array of these actuators, bonded to the back surface of a thin, flexible mirror face sheet, could push and pull individual points on the mirror surface with nanometer precision at update rates of hundreds to thousands of times per second. The mirror could be made to adopt almost any smooth surface shape within its mechanical range, and it could change that shape continuously, tracking the atmosphere as it evolved. The wavefront sensor that told the mirror what shape to adopt was based on a design proposed by French physicist Roland Schack and American optical engineer Ben Platt in 1971, building on earlier work by Johannes Hartmann from 1900. The Schack-Hartmann wavefront sensor divides the incoming beam into an array of small sub-apertures using a lenslet array, a grid of tiny lenses, each approximately 1 millimeter across, and focuses each sub-aperture onto a detector. A flat, undistorted wavefront produces a regular grid of focal spots on the detector. A distorted wavefront causes each sub-aperture's focal spot to shift from its reference position by an amount proportional to the local slope of the wavefront at that sub-aperture's location. Measuring the displacement of every spot in the grid simultaneously gives a complete map of the wavefront slope across the full aperture. From this slope map, the wavefront shape itself can be reconstructed mathematically in milliseconds. The control computer, the brain of the system, takes the reconstructed wavefront, calculates the mirror actuator commands required to flatten it, and sends those commands to the deformable mirror, all within a single control cycle. The mirror deforms. The wavefront is corrected. The sensor measures the residual error. The mirror adjusts again. The entire loop, sense, compute, correct, runs continuously at rates between 100 and several thousand cycles per second, chasing the atmosphere as it evolves, never quite catching it perfectly, but always staying close enough to reduce the wavefront error to a small fraction of a wavelength. The first military adaptive optics systems achieved results that startled even their designers. Ground-based telescopes equipped with early adaptive optics hardware resolved features on satellites and missile bodies that had previously been undetectable. The resolution gains were not marginal improvements. They were transformative. A telescope that had been seeing limited at 1 arc-second was suddenly delivering images approaching its diffraction limit, in some cases improving image sharpness by factors of 10 to 20 in a single step. Decades of atmospheric sealing dissolved in milliseconds of mirror correction. All of this happened in complete secrecy. The astronomical community had no access to the results, no knowledge of the hardware, and no way to build on the advances being made inside classified facilities. The parallel between military surveillance and astronomical imaging was total. The physics was identical, the hardware was directly applicable, but the wall between classified defense research and open science was absolute. That wall cracked in 1991 when the United States Department of Defense declassified a substantial portion of its adaptive optics research following the end of the Cold War. The declassification announcement was made at an American Institute of Aeronautics and Astronautics conference in March of that year. Within months, astronomers who had spent careers accepting the atmospheric ceiling as a fundamental, immovable limit were reading technical reports describing hardware that had been quietly eliminating that limit for over a decade. The response from the astronomical community was immediate and electric. The European Southern Observatory, which had been independently developing adaptive optics technology in collaboration with the French aerospace research agency ONERA and the Laboratoire de Marcoussis, had already demonstrated the first civilian astronomical adaptive optics system in October of 1989 at the Observatoire de Haute-Provence in France. That system, the VLT adaptive optics prototype, had achieved diffraction-limited imaging at infrared wavelengths of 3.5 micrometers and longer on the observatory's 1.52-meter telescope. The results were published in the scientific journal Astronomy and Astrophysics and reviewed in Nature. An editorial in Nature called it a major breakthrough, but the infrared limitation was significant. At 3.5 micrometers, the Fried parameter is larger relative to the wavelength of light than at visible wavelengths. The atmosphere is effectively less turbulent in the infrared, making correction substantially easier. Pushing adaptive optics correction into the visible wavelength range below 1 micrometer required wavefront sensors and deformable mirrors operating at far higher speeds and with far higher actuator densities. A visible light system on an 8-meter telescope would require a deformable mirror with thousands of actuators, a wavefront sensor measuring thousands of subapertures simultaneously, and a control loop running at several thousand hertz. None of that existed in 1989. It was the next engineering frontier. There was also a deeper, more fundamental problem that no amount of engineering speed could solve directly. Adaptive optics requires a reference source, a bright point of light near the science target whose wavefront distortions can be measured and used to drive the mirror corrections. This reference source is called the guide star. For the correction to be valid, the guide star must lie within the isoplanatic angle of the science target. The angular radius within which the atmospheric turbulence is sufficiently correlated that a correction derived from the guide star applies accurately to the science target. At visible wavelengths over a typical observatory site, the isoplanatic angle is approximately 5 to 15 arcseconds. A circle 5 arcseconds in radius covers less than 1/millionth of the total sky area. The fraction of interesting astronomical targets that happen to have a sufficiently bright natural star within that tiny circle is vanishingly small. Adaptive optics corrected with natural guide stars could only be used for a small percentage of science cases. The solution to this problem was as audacious as any proposal in the history of observational astronomy. If a sufficiently bright natural star was not available, one could be created, artificially, using a laser. A powerful laser beam, tuned to a wavelength of 589 nanometers, precisely the wavelength absorbed and re-emitted by sodium atoms, could be projected from the telescope into the atmosphere. At an altitude of approximately 90 kilometers, in a thin layer of the mesosphere where meteoric ablation deposits a permanent reservoir of free sodium atoms, the laser excites those atoms to fluorescence. They re-emit the laser light, creating a glowing spot 90 kilometers above the telescope. From below, this spot is indistinguishable from a faint star. It is artificial. It is positioned exactly where the telescope needs it, and it can be created for virtually any target in the sky. The concept of the laser guide star had been proposed independently in the 1980s by Will Happer at Princeton University, and in classified work by researchers at the Lawrence Livermore National Laboratory. when the declassification of 1991 made the classified laser guide star proposals public. They merged with the civilian astronomical adaptive optics programs in a collision of ideas that reshaped the entire field within a decade. The first sodium laser guide star system used for astronomical adaptive optics was demonstrated at the Lick Observatory on Mount Hamilton in California in 1996. The laser beam projected from the 3-meter Shane telescope into the night sky was visible from the ground as a thin orange beam climbing vertically into the dark. The same sodium yellow that colors a flame when salt is burned, now stretched into a column 90 kilometers long and terminating in an artificial star above the mesosphere. It worked. The science targets that had been inaccessible to adaptive optics correction, the galactic center, distant galaxies, star-forming regions without nearby bright stars, were suddenly within reach. The sky had not changed, the atmosphere had not changed, but humanity's ability to see through it had crossed a threshold from which there was no going back. The center of the Milky Way is hidden. Not by distance alone. The galactic center sits approximately 26,000 light-years from Earth, a distance so extreme that light leaving it during the last ice age is only now arriving at our detectors, but by an almost impenetrable curtain of interstellar dust and gas that absorbs virtually all visible light passing through it. The optical depth of the dust along the line of sight to the galactic center is so severe that visible light is attenuated by a factor of approximately 1 trillion. 1 trillion times dimmer than it would be without the dust. No optical telescope, regardless of aperture or atmospheric correction, can see the galactic center in visible wavelengths. It is, to the human eye and to every camera built to mimic it, completely invisible. Infrared light passes through dust far more efficiently than visible light. The extinction at 2.2 micrometers, a near-infrared wavelength known to astronomers as the K-band, is only about 1/30th of what it is in visible light. Not zero, but workable. A sufficiently sensitive infrared detector behind a sufficiently large telescope with sufficiently good atmospheric correction could in principle peer through that curtain and see what lay behind 30,000 years of accumulated cosmic obscuration. What lay behind it was one of the most extreme environments in the observable universe. The first evidence that something extraordinary occupied the galactic center came not from images, but from radio waves. In 1974, Bruce Ballack and Robert Brown, working with the National Radio Astronomy Observatory's interferometer at Green Bank, West Virginia, detected a compact, extraordinarily bright radio source at the exact position of the galactic center. It was unresolved at radio wavelengths, smaller than the beam of their instrument could measure. It was also stationary relative to the background of distant galaxies, meaning it was not moving with the normal stellar motions of the galactic disk. They called it Sagittarius A star. The asterisk notation indicated a particularly interesting or peculiar source in radio astronomy cataloging convention. The name stuck. What Sagittarius A star was could not be determined from the radio data alone. It was compact, luminous in radio emission, and gravitationally anchored at the dynamical center of the galaxy. These properties were consistent with a massive black hole, an object predicted by general relativity, never directly observed, and still theoretically controversial in 1974. The evidence was suggestive. It was not proof. Proof required measuring the gravitational influence of the object. Specifically, it required watching stars move. Stars near the galactic center orbit whatever mass is concentrated there, just as planets orbit the sun. The orbital velocity of a star, combined with the geometry of its orbit, encodes the central mass directly through the same Keplerian mechanics that Johannes Kepler extracted from Tycho Brahe's planetary observations in the early 17th century. If the stars near Sagittarius A star could be observed over years or decades, their orbits could be mapped, and the enclosed mass calculated. The problem was resolution. 26,000 light-years away, the region within 1 light-year of the galactic center subtends approximately 8 arcseconds in the sky. Individual stars within that region are separated by milli-arcseconds. No ground-based telescope, even on the best night at the best site, could resolve individual stars inside that region without adaptive optics correction. 2 teams began the work in the early 1990s, independently and in competition. One was led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Garching, Germany, working with the New Technology Telescope and later the Very Large Telescope at the European Southern Observatory in Chile. The other was led by Andrea Ghez at the University of California, Los Angeles, working with the 10-meter Keck telescopes on Mauna Kea in Hawaii. Both teams used near-infrared cameras operating behind adaptive optic systems. Both pointed at the same patch of sky, the inner arcseconds surrounding Sagittarius A star. The observations began with simple imaging. Individual stars near the galactic center, invisible in previous seeing-limited observations, resolved into distinct points under adaptive optics correction. In the very first corrected images, what had appeared as a diffuse smear of unresolved light fractured into dozens of individual stellar sources, crowded together in a volume of space unlike anything seen elsewhere in the galaxy. The stellar density in the central parsec, a parsec being 3.26 light-years, exceeds the stellar density in the solar neighborhood by a factor of approximately 1 million. 1 million stars packed into a volume that would contain fewer than 10 in the Milky Way's suburbs. The galactic center is not empty. It is catastrophically full. From those first resolved images, both teams began the process of proper motion measurement, tracking the positions of individual stars from year to year, measuring how they moved across the sky. The stars near Sagittarius A star moved fast, extraordinarily fast. A star designated S2 by Genzel's team, also known as SO2 in Gez's notation, appeared to be orbiting the central radio source at velocities reaching several thousand kilometers per second at closest approach. For reference, Earth orbits the Sun at approximately 30 kilometers per second. The stars at the galactic center were moving at roughly 200 times that speed. As the years accumulated and the orbital arcs lengthened, the shape of S2's orbit became measurable. It was an ellipse, precisely as Kepler's first law demands for any bound gravitational orbit. The ellipse had a semi-major axis of approximately 120 astronomical units. 1 astronomical unit is the mean distance from Earth to the Sun, approximately 150 million kilometers. S2's orbit, at its widest, spans a region roughly 120 times the Earth-Sun distance. Its orbital period, the time required to complete one full revolution, is approximately 16 years. 16 years to complete one orbit around whatever sat at the galactic center. Plugging these numbers into Newton's version of Kepler's third law, which states that the square of the orbital period is proportional to the cube of the semi-major axis, with the proportionality constant set by the central mass, gives a result of staggering magnitude. The mass enclosed within S2's orbit, the mass that must exist at the center of that 16-year ellipse to generate the observed orbital velocities, is approximately 4 million times the mass of the Sun. 4 million solar masses, confined, based on the compactness of the radio source and the orbital dynamics, to a volume smaller than our solar system. Nothing known to physics other than a black hole can pack 4 million solar masses into a space that small. A star cluster of 4 million ordinary stars would be gravitationally unstable at that density. Stellar collisions and tidal disruption would destroy it in a fraction of the galaxy's age. A concentration of dark matter would not produce the compact radio emission observed from Sagittarius A star. The object could not be a neutron star. The maximum mass of a stable neutron star, set by nuclear physics and the equation of state of dense matter, is approximately 3 solar masses. 4 million solar masses in the volume of a solar system means a central density exceeding 10 to the power of 22 kilograms per cubic meter. The event horizon radius of a 4 million solar mass black hole, the Schwarzschild radius, equal to 2 times the gravitational constant times the mass divided by the square of the speed of light, works out to approximately 12 million kilometers, roughly 1/10 of an astronomical unit. A sphere 12 million kilometers across. Smaller than the orbit of Mercury around the Sun, containing 4 million times the mass of the entire Sun. Both Genzel and Ghez refined their measurements over 2 decades. The orbits of not one but dozens of stars near Sagittarius A star were mapped in full. S2 completed a full observed orbit between 1992 and 2008, and again between 2008 and 2023. At its closest approach to Sagittarius A star, a point called periapsis, S2 passes within approximately 120 astronomical units of the black hole and reaches a velocity of approximately 7,600 kilometers per second. That is approximately 2.5% of the speed of light. Relativistic effects become measurable. The orbit precesses. The ellipse's long axis rotates slightly with each orbit, exactly as Einstein's general relativity predicts for motion in a strong gravitational field. The precession measured for S2 is consistent with general relativity to within the measurement uncertainties. In 2020, the Nobel Committee awarded the Nobel Prize in Physics jointly to Roger Penrose for theoretical work on black hole formation and to Reinhard Genzel and Andrea Ghez for the observational discovery of a supermassive compact object at the galactic center. The Nobel citation specifically credited the decades of adaptive optics-enabled infrared observations at the galactic center as the experimental foundation of the award. The prize acknowledged without ambiguity that the answer to one of the deepest questions in astrophysics, whether supermassive black holes truly exist at the centers of galaxies, had been obtained by pointing ground-based telescopes at a region of sky no larger than a thumbnail held at arm's length, correcting for the shimmer of Earth's atmosphere in real time and watching stars move. Then, in April of 2019, something happened that shifted the entire conversation. The Event Horizon Telescope Collaboration, a global network of radio observatories spanning from Hawaii to Chile to Greenland to Antarctica, linked by precise atomic clocks and connected through a technique called very long baseline interferometry, released an image, not of the galactic center's Sagittarius A star, that image came later, in 2022, but of the supermassive black hole at the center of the galaxy, Messier 87, 55 million light-years from Earth. The image showed a bright asymmetric ring of radio emission surrounding a central dark region. The dark region was the black hole's shadow, the zone within which the gravitational field was so intense that no photons on trajectories passing close enough to the event horizon could escape to reach the detector array. The shadow's angular diameter was approximately 42 micro-arcseconds, 42 millionths of 1 arcsecond. To resolve it required a telescope effectively the size of Earth itself. The ring was not uniform. The southern arc was brighter than the northern arc, exactly as general relativity predicts for a black hole rotating in a particular direction, whose relativistic jet is observed to point toward Earth. The brightness asymmetry arises because material in the accretion disk on the side moving toward the observer is Doppler boosted, its radio emission amplified, while material on the receding side is suppressed. The image encoded in its asymmetry the rotation state of an object 55 million light-years away and 6.5 billion times the mass of the Sun. 6.5 billion solar masses. If our Sun were replaced by the black hole at the center of Messier 87, its event horizon would extend past the orbit of Neptune, the outermost major planet in our solar system, orbiting at 30 astronomical units from the Sun. The entire solar system, every planet, every asteroid belt, every comet in the Kuiper belt would fall within the event horizon. Swallowed. Gone. And yet the image of this object, obtained not by a single telescope, but by the coordinated atomic clock-synchronized observations of radio dishes on multiple continents, was released to the public on a Wednesday morning. It fit on a screen. It was shown at simultaneous press conferences in Brussels, Santiago, Shanghai, Tokyo, Washington, and Taipei. The first direct visual evidence of a black hole event horizon, an object predicted by Einstein's field equations in 1915, theorized about for over a century, and now photographed, was shared with the world in the same hour it was shown to scientists. The stars had not changed. The physics had not changed, but the instruments had finally become worthy of the universe they were trying to see. There is a photon traveling toward Earth right now that left a star in the Andromeda galaxy 2.5 million years ago. When it departed, the species that would eventually build telescopes to receive it did not yet exist. Homo habilis, the earliest stone tool-using member of the genus Homo, would not appear in the fossil record for another 500,000 years. The photon crossed the local group of galaxies, passed through the intergalactic medium, entered the Milky Way's outer halo, threaded its way through 2.5 million light-years of mostly empty space, and arrived at the top of Earth's atmosphere traveling at 299,792,458 meters per second, the same speed it had when it left. Unchanged. Carrying in its polarization state, its precise wavelength, and its arrival time, information encoded at the moment of its emission about the physical conditions in the star that produced it. Then it hit the atmosphere. In the final 100 kilometers of a 2.5 million light-year journey, it encountered the turbulent, churning, thermally unstable ocean of gas that clings to this planet's surface. The same atmospheric layer that produces weather, that sustains oxygen-breathing life, that filters lethal ultraviolet radiation from the sun, that same layer spent the photon's final milliseconds of travel distorting its wavefront, bending its path by fractions of an arcsecond, mixing it with thousands of other photons arriving from slightly different directions through slightly different atmospheric columns, and delivering it to whatever detector happened to be pointed in that direction at that moment. For most of human history, the detector was an eye, a biological instrument of extraordinary sensitivity. The dark, adapted human eye can detect as few as 5 to 7 photons arriving within a brief time window, a sensitivity threshold so low that it approaches the fundamental quantum limit of light detection. But the eye cannot record. It cannot accumulate photons over hours of exposure. It cannot subtract backgrounds, measure wavelengths to parts per million, or track the position of a star to milli-arc-second precision over decades. The eye is a magnificent instrument for survival. It was never optimized for cosmology. The history of astronomy is, at its core, the history of extending the eye. The telescope extended its reach in 1609. Photography extended its memory in the 1840s, when John William Draper obtained the first successful photograph of the moon through a telescope, and later when Henry Draper, his son, obtained the first photograph of a stellar spectrum in 1872, recording in silver halide what no eye could hold. Electronic detectors replaced photographic plates beginning in the 1970s and 1980s, bringing quantum efficiencies, the fraction of incoming photons that are actually detected, from the 2 to 4% of photographic film to above 90% for modern charge-coupled devices. Each step in this progression was a step toward receiving, faithfully and completely, the information that the photons had been carrying for millions of years. Adaptive optics was a different kind of step, not an extension of reach, but a removal of corruption. The photon from Andromeda, or from the galactic center, or from the accretion disk of a supermassive black hole 55 million light-years away, arrived at the telescope carrying pristine information. The atmosphere had scrambled the wavefront. Adaptive optics unscrambled it. Not perfectly, never perfectly, but sufficiently to recover the diffraction-limited resolution that the telescope's aperture theoretically deserved. It was, in a precise physical sense, the act of restoring a message that interference had garbled. The information was always there. The technology finally became capable of reading it. The James Webb Space Telescope launched on December 25, 2021, and reaching its operational orbit around the second Sun-Earth Lagrange point, a gravitationally stable location approximately 1.5 million kilometers from Earth in the direction away from the Sun, represents the ultimate expression of the other solution: leave the atmosphere entirely. Webb's primary mirror spans 6.5 meters, composed of 18 hexagonal beryllium segments coated with a microscopically thin layer of gold, chosen for its exceptional reflectivity at infrared wavelengths. Operating at a temperature of approximately minus 233 degrees Celsius, just 40 degrees above absolute zero, Webb's detectors are sensitive to infrared wavelengths between 0.6 and 28 micrometers. At those temperatures, the telescope itself emits negligible thermal infrared radiation, allowing it to detect the faint heat signatures of objects at cosmological distances without its own thermal noise drowning the signal. Webb's angular resolution at 2 micrometers is approximately 0.066 arcseconds. From its vantage point above every molecule of Earth's atmosphere, this resolution is limited only by diffraction, by the wave nature of light and the finite size of the mirror. No seeing disk, no fried parameter, no Kolmogorov turbulence cascade. The atmosphere's 4,000-year interference with astronomical observation simply does not exist at the second Lagrange point. The photons arrive, the mirror collects them, the detectors record them. The physics is clean. Webb's first deep field image, released publicly on July 12, 2022, by United States President Joe Biden at the White House, showed a patch of sky approximately the angular size of a grain of sand held at arm's length. Within that patch, smaller than 1/10,000th of the full sky, Webb resolved thousands of individual galaxies. Galaxies at redshifts exceeding 13, meaning their light was emitted when the universe was less than 400 million years old, less than 3% of its current age of approximately 13.8 billion years. The most distant confirmed galaxy detected by Webb as of early 2026 has a spectroscopic redshift, placing its light emission at a time when the universe was approximately 290 million years old. The photons in that observation had been traveling for over 13.5 billion years before striking Webb's gold-coated beryllium mirror. The twinkling that a child sees looking up at a clear night sky and the image of a galaxy 13 billion light-years away are connected by a single, unbroken thread of physics. Both involve the same photons. Both involve the same wavefront distortion. The child's eye receives the scrambled atmospheric output and perceives beauty. A shimmering, living sky that human cultures across every continent and every recorded era have interpreted as divine, as navigational, as narrative, as wonder. The adaptive optics system and the space telescope receive those same photons, or photons from the same sources, and extract from them the mass of a black hole, the age of the universe, the chemical composition of a stellar atmosphere 40 light-years away, the presence of water vapor in the atmosphere of an exoplanet orbiting another star. Neither experience is more valid than the other. They are measurements at different resolutions of the same physical reality. The question that opened this documentary, why do stars twinkle and why do planets not, resolves into something far larger than atmospheric optics once its full implications are traced. The twinkling is a symptom. The disease is the atmosphere's intervention between the observer and the universe. The treatment is a century of physics, engineering, mathematics, and the focused labor of thousands of scientists on multiple continents building instruments capable of compensating for or escaping a layer of gas 100 kilometers thick. The result of that treatment is a species that can now image the shadow of a black hole 6.5 billion times the mass of the sun, measure the orbital precession of a star moving at 2.5% of the speed of light around an invisible 4 million solar mass object at the center of the galaxy, and photograph individual galaxies as they existed when the universe was a 3% complete draft of what it would become. The extremely large telescope, currently under construction on Cerro Armazones in the Chilean Atacama Desert at an altitude of 3,060 meters, will have a primary mirror 39.3 meters in diameter. 39.3 meters. Wider than a standard Olympic swimming pool is long, which measures 50 meters, giving some sense of the scale. Its adaptive optics system will use 6 deformable mirrors and multiple laser guide star constellations to correct for atmospheric turbulence across a wide field of view simultaneously. At its design wavelengths, it will achieve angular resolutions of approximately 1 milliarcsecond, 1,000th of an arcsecond, from the ground. It will image the surfaces of nearby stars as resolved disks. It will directly photograph Earth-sized exoplanets in the habitable zones of nearby stars and analyze the chemical composition of their atmospheres through spectroscopy. If oxygen, water vapor, methane, and carbon dioxide are found simultaneously in the spectrum of an exoplanet atmosphere, it would constitute the strongest evidence yet obtained for the existence of biological processes beyond Earth. All of this, the galactic center orbits, the black hole image, the Webb deep fields, the extremely large telescope's future exoplanet atmospheres, traces back to the same foundational question. Why does light bend when it passes from one medium to another? Why does the refractive index of air vary with temperature? Why do stars, being point sources, twinkle when planets, being extended disks, do not? The answers to those questions, pursued rigorously and without compromise across 4 centuries, led from a Galilean refractor with a 20-power magnification to a 39-meter mirror in the Atacama. From naked eye scintillation to adaptive optics, feedback loops running at 3,000 hertz. From the observed fact of starlight trembling in the dark to the measured orbital velocity of a star moving at 2.5% the speed of light around a 4 million solar mass singularity. Science does not always proceed from grand visions toward small confirmations. Sometimes it moves the other way. From a small, precise, observable fact toward a question so large, it restructures the entire frame of human knowledge. A star trembles in the night sky. The question of why it trembles, followed wherever the physics leads, without detour and without surrender, ends at the edge of a black hole. That is where curiosity goes, when it is given enough time and enough instruments, and enough people unwilling to accept that the sky is simply how it looks. It goes all the way to the end of the light.